So we've looked at how to add vectors together. Now we're going to look at how to multiply two vectors together. And there's two ways that we look at of doing this. There's what they call the scalar product or the dot product, and there's the cross product. So we look first at the scalar product or the dot product of two vectors. Dot product, because when you write it down, we write A dot B to mean the dot product of the vectors A and B. And the definition is simple. It's the magnitude of A times the magnitude of B times the cosine of the angle between them. So if I have two vectors, let's say A and B, the angle between them we call theta. A dot B is equal to the magnitude of A times the magnitude of B. Remember, those are just scalars, they're just numbers, times the cosine of theta, the angle between them. And where we might use the scalar product is to find that angle, because of course that would imply that the cosine of theta is equal to A dot B divided by the two magnitudes. So thereby we could find cosine theta, and knowing cosine theta we can find theta, the angle. Of course, to do this we need a way of calculating A dot B that doesn't require us to already know theta, but we'll get to that in a second. We might also want to just show that two vectors are orthogonal. Orthogonal means at right angles to each other. So orthogonal vectors have a dot product of 0, because of course cosine of theta, cosine of 0 is equal to 0. So if I have two vectors at right angles to each other, that's a right angle. That means that theta is equal to 0, and so cosine of theta is 0, and so the dot product is 0. So orthogonal vectors are vectors at right angles to each other, or they're vectors whose dot product is 0. And that's what's said here in this remark. If A and B are orthogonal, i.e. if A is orthogonal to B, that's what that little symbol here means. You see it's two perpendicular lines. Then we have that the dot product is equal to magnitude of A times magnitude of B times the cosine of 90 degrees is equal to 0. Here's another remark. If A and B are parallel, that's what this little symbol means, two parallel lines, A is parallel to B. Then we have the dot product A and B is equal to magnitudes multiplied together times the cosine of 0. So if they're parallel, the angle between them is 0. The cosine of 0 is 1. So the dot product of two parallel vectors is just the product of their magnitudes. Next, let's look at doing the dot product with vectors that are broken up into their component vectors. So I, j and k here are the unit vectors in the x, y and z directions. So we've broken up A into A1, A2 and A3, the components. So A is equal to A1 times I plus A2 times j plus A3 times k. And B is equal to B1 times I plus B2 times j plus B3 times k. And then we evaluate the scalar product. So I'll just take it for granted for the moment that when we take the scalar product of two sums of vectors, or vectors broken into their components, that we multiply it out in the way you'd normally expect. So if I multiply out this thing, the first term I get is I have A1 times I times B1 times I. So I get A1 B1 times I dot I. The next term, or let's pick a random term. Let's take the one that I get from multiplying A2j times B3k. I would get A2 times B3 times j dot k, which I get here. So all of these terms I get just by multiplying out those two sums of components. But then when I look at this big long sum that I have, the first thing I'd notice is that I, j and k are all perpendicular to each other. They are components or vectors in the x, y and z directions. So anywhere I see I dot j, I dot k or k dot j, dot products of these mutually perpendicular unit vectors, the product will always be 0. So take I and j for example. I is in the x direction, j is in the y direction. So I dot j is equal to the magnitude of I times the magnitude of j times the cosine of 90 degrees. The magnitude of I is 1 and the magnitude of j is 1. They're defined that way as unit vectors. So that's 1 times the cosine of 90 degrees, which is 0. And so I get 0. So that's that line here. The other thing I have is that, what about I dot I or j dot j or k dot k? Let's look at I dot I. That's equal to the magnitude of I times the magnitude of I times the cosine of 0 degrees. That's equal to 1 times 1. The cosine of 0 degrees is 1. So that's 1. So I dot I or j dot j or k dot k are all equal to 1. So if I substitute that back into that formula above, most of those terms are just 0 because they have I dot j or I dot k or whatever. And the rest of them, the dot product part is just 1. And so in the end we just get left with a dot b is equal to a1 times b1 plus a2 times b2 plus a3 times b3. So once I have the components of two vectors and I want to get the dot product, all I'm doing is multiplying the first two components together and the second two together and the third two together, and I'm adding them all up. You might notice that it looks a little bit like matrix multiplication, in that if I were to write down my components like this in a matrix, my A is here and my B is here, and I were to multiply these two matrices together, that's a 1 by 3 and a 3 by 1, giving me a 1 by 1 as my answer. The answer would just be a1 times b1 plus a2 times b2 plus a3 times b3, which is exactly what I got for that dot product above. You might have heard me in previous lectures talking about a 1 by 3 matrix like the a1 on the left there as a row vector, or the 3 by 1 matrix like the one there on the right, the b1, as a column vector. And that's why. It's because vectors are often represented as matrices with only one row or column. And if you multiply a row vector by a column vector, essentially what you're doing is taking this dot product. This connection between vectors and matrices isn't that important for the calculations we're doing for the moment, but it's worth pointing it out. And it's at least worth telling you why I've been calling some matrices row vectors or column vectors. And it's just worth noticing this for the moment. So that is the dot product. The dot product is something that comes up absolutely all the time in engineering and in all kinds of practical applications. It's absolutely central to anything that you do with vectors. So if you haven't quite followed everything that's gone on in this video, have a read through the notes again and watch the video again, because you really do need to know this, and you definitely will be seeing this again in all kinds of places. So that's the vector dot product, or the scalar product. I forgot to mention it's called the scalar product because what you get out of it is a scalar, or just a number. So the next vector product we'll be looking at will be what's called the cross product, or the vector product, where we take two vectors, we multiply them together and we get another vector. So that will be the next video.